All right, now behave. Don't overheat. I mean, I went to Walmart yesterday and got all right, so what we talked about Wednesday is primarily we talked about mass. I'm not going to go back and review what we talked about on KVP. We're just going to talk about mass. So we talked about mass, how we control mass at the console, what it is that we're actually controlling with separately with MA and time. We took a look at where the different components are on the circuit. We took a look at the MA circuit, the truly low voltage circuit, and we just call that the MA circuit. It's that lower portion of the circuit. When we talked about how that works, we talked about step up transformer being, a higher turns ratio, more turns on the secondary side than the primary side, but that step down transformer has more turns on the primary side than the secondary side. So it works off of low voltage, as low as 12 volts, and that's to keep it from the electrons from jumping from cathode to anode before we make our exposure time. We talked about the timer circuit being on a different circuit in the low voltage circuit in the primary circuit on the low voltage side. So we talked about mass not occurring until we make that exposure. We talked about the calculation of mass. We're going to talk in depth about that with our reciprocity and our changes of MA and time to get to different mass values. So we talked about what we call mass. Mass is just the number of electrons that we create. There's a number of electrons we send that directly affects the number of X-rays that get put out from the X-ray tube. So what MA controls in the X-ray tube is the heating of the filament, remembering that we've always got current through the filament present. It just doesn't get to the point of thermionic emissions until we press the prep button. Then we talked about mass again being directly related to the amount of X-rays we send, and therefore the number of electrons we send, and therefore the number of X-rays that we create. So increased mass gives us two things: a higher current and, of course, more heat. So changes in mass directly proportional to emission, creation, and emission, and it's equal at all energy levels. All changes are proportional to the changes in mass. So then we talked about how we can change our exposure with an increase in MA and decrease in time. Increase in time and decrease in MA we would use for breathing techniques, but if we use too long a time, we wind up with a motion artifact. So we talked about the Brim spectrum. We're just going to get to the Brim spectrum. With mass, all we get is an increase in numbers. We don't get an increase in peak. It doesn't do anything to affect the minimum energies. It doesn't do anything to affect the position of the average, even though on this diagram it seems to me that it kind of lowered the average. Just ignore that, pay attention, no attention to the man behind the curtain. Just make believe that if you were to draw a line straight up from here, then it would be there as well. Okay, and it does nothing for our characteristic spectrum. So we talked about what we will talk about then this semester is the effects of changing. We talked about all that, so I'm not going to run through all that. Then we got into voltage rectification, and that is the process of changing alternating current to pulsating direct current, and it occurs after the high voltage transformer because the transformers have to have alternating current to work. We can't do it anywhere else. It has to be after that. So how does it affect tube output? And that would be as we go from single phase to three phase, we get an increase in tube output. If we go from half wave to full wave rectification, we get an increase in output. And then if we go from three phase to single to high frequency, we again get a little bit of a bump in output. So we talked about 3 types of generators, just mentioned those. Voltage ripple is just how far the voltage drops in between each one of those pulses. And we talked about the voltage ripple being 100%, 14%, 3% less than 1%. As we go from single phase, 3-phase 6 pulse, 3-phase 12 pulse, and high frequency. Most common type that you're going to be working with would be the high frequency. So again, we looked at the Brim spectrum between the 3 and with the change in generator type, so single phase, what we get is no change in peak, no change in minimum. We do get a change in output. That output is numbers. Numbers is represented by the area underneath the bubble, and it does move now towards the high energy side. So single phase, less output, lower average. With 3-phase, the average increases, high frequency it increases again. So that brings us up to today, and what we're going to talk about this semester regarding rectification is we're going to talk about technical factors and how the technical factors need to be adjusted pretty much for our changes in generator type. So remember, you're not going to have 2 different generator types on the same machine, so you're talking about 2 different rooms. So we're going to talk about effects of voltage rectification on patient exposure, on IR exposure, on image quality. And I'm going to say this over and over again. I got to throw it in there, image quality. It really doesn't have that much of a change except for potentially 2 things. One is that the higher the output, like if we go from single phase to 3-phase, we can cut back on our exposure so we can get shorter exposure times, and that would reduce the likelihood of motion artifact, right? But also, and again, we kind of beat this to death, that the unlikelihood that you're going to see quantum model, we still have to talk about it, and that would be that just remember that anything that reduces mass could potentially introduce quantum model, right? So in a theoretical world, it could introduce quantum model because our mass is going to get low. Okay, so we're going to talk about technical compensation for each, and we're going to talk about potential image quality issues. We just did that, but we'll talk about it again. So what does rectification change? AC to DC. We just talked about where it occurs, why it occurs there. It keeps the inverse voltage from damaging the X-ray tube, specifically the filament. So we talked about what it does to the Brim spectrum as well. So it's not changeable in any given machine. Your generator is your generator. It increases the average without increasing the peak. It pushes towards the high energy side. It changes changing machine phases requires a change in technique, and we're going to really hammer that this semester. And increasing machine phase improves the quality of the X-ray beam. X-ray beam quality and image quality don't always, they're not always the same thing. And then we talked about voltage ripple, and you just got to know the numbers on those. So now we get into X-ray tubes. So you've got 2 different types of X-ray tubes, and within those 2 types of X-ray tubes, you have one that has multiple types of X-ray tubes. So fundamentally, you've got 2. You've got stationary and you've got rotating anodes. And this is where I'm going to go back to this view so that you can see the notes if you want to. So you've got stationary anodes and you've got rotating anodes. What we use is a rotating anode, and the reason for that is because we want to change the area of bombardment of the electrons. So if we use a stationary anode, we hit the anode with the electrons in exactly the same space for the life of the X-ray tube. And since heat is the main thing that we create in the X-ray tube, and it's the main thing that we're going to deposit on the anode, then naturally our anode life is going to be reduced. So we don't want that. So we want to change that target area. So we're going to use a round anode, and we're going to rotate it quite quickly. in order to change that area. Also with that, what it's going to enable us to do is use a bigger disc or a bigger overall target area is going to increase that exponentially, but it's also going to give us a big fat metal thing that we can send some of that heat to. So if we have an overall disc or an overall target area that's the size of a quarter, then it's only going to get so hot before it melts, right? But if we have one that's the size of a small dinner plate, saucer plate or whatever, then that heat can spread out a whole lot more, and it extends the life of the X-ray tube. So we rotate it to change that point of bombardment, and the whole anode is not the target. Remember, we've got several different parts to the anode, some of which aren't even inside the X-ray tube, right? So what rotates the anode is an electromagnet, and it's on the outside of the glass. It's inside of the protective housing, but it's outside of the glass, right? So it's you're going to see test questions that say what's the only part of the X-ray tube that is outside of the envelope, and that would be your stator. Stator means stationary; it doesn't move. It works off of electromagnetic induction, and those electromagnets fire in a specific sequence to accelerate that anode. And it goes from stationary up to 3,000 RPMs within about a second. That's why when you press your prep button, you hear it start up, but you can't make an exposure for a little while. That's why I say if you've got a kid, a little crying kid that you're trying to take a chest x-ray on, you've got to be on that prep button. Even though it's bad for the X-ray tube, you have to be on that prep button because they're going to take that really quick inhalation, and you got to make your exposure right then, right? So if you wait until that and you push your exposure switch, you'll get an exposure, but it's not going to be until a second after you push it so that it gets the rotor up to speed. So the whole target is not that. The target is not the entire anode. The anode is the entire assembly, including the bearings that it spins on. So this is one of the slides that I added stuff to this morning. I don't want to make that too small. So the rotor is everything that rotates. The stator is everything that does not rotate. So the rotor rotates on those bearings, and we talked about that last semester. And the bearings, if they get too hot, then they can kind of melt. And we talked about how you can tell that. It starts to grind. We used kind of an analogy. You're driving down the road and you hear cars, they got wheel bearings that go out, and it makes a grinding sound. It's the same sound that you're going to hear out of your X-ray tube. It doesn't mean that the X-ray tube has to be replaced right now, but it's coming up. Eventually those bearings are going to get so wore out that it's going to stop, and once it stops, we're working on an X-ray tube with a stationary anode, and we've just talked about that. If we have stationary anode, you're eventually going to melt it. So the stator, we talked about that. It's outside of the X-ray tube. It works off the principle of electromagnetic induction, provide electricity, creates a magnetic field, and it drags that anode around in a circle. So the target is just the area of bombardment. So the entire disk is not the target. The disk is the disk. The target is the focal tract where we actually get the area of bombardment, the focal tract. But the graphite backing on the target, on the disk, that's one thing that we do to try to keep the heat off of the bearings. Keep it off of the bearings, it extends tube life. So target made of tungsten is tungsten alloy. We talked about that last semester. Pure tungsten is brittle, so if you drop, you bang around the tube enough, it could damage it. All right, so now I'm going to extend this back down. All right, so how do we get to tube failure because of heat on the anode? And primarily it's going to be two things. One is going to be hot exposure on cold anode, and that is where we're going to get cracking of the anode. And then the other is overheating of the bearings, wearing that lube out on the bearings. And if that happens, they start to grind, and eventually they'll stop the anode from rotating. So on the cathode end, go back down. So the cathode end is where we have our filament and our focusing cup. We have a tendency to overlook the focusing cup. The purpose for the focusing cup is to compress that stream of electrons so that it hits the target area that we want it to hit. Without the focusing cup, the X-rays would be created over a much larger area, and we lose sharpness of recorded detail. So remember that the purpose for the filament is to give us our sharpness of recorded detail. Where we want very good detail, we use a small filament. If we're the problem with the small filament is that you can only make certain exposures on it, and that is built into the system. That's a computer in the system trying to prevent you from harming the X-ray tube. So if you try to put too many electrons on that small filament, then you burn out the filament, and you can't make high resolution X-rays anymore. You can still use large filament, you just can't use a small filament. So that's built into the system. It's exposure limited. You can't make an exposure, 500 mass exposure on a small filament. You're just not going to be able to do it. If you even try to select a MA station above 200, it's going to give you tube overload. Okay, so if you're setting a technique, that's the first thing you should look at. Is that if you set a technique and it's a relatively large technique and you have tube overload, and you know it's a room you haven't been overusing, then take a look at your focal spot size and your MA station. Chances are there's a very good chance you're on a small focal spot with too high of an MA station. So we have two, one for high heat load and one for high detail. So if you're looking for trabecular markings in the fingers and things like that, you're going to use that small filament. They're made from tungsten as well for all the reasons we talked about last semester. It can take a lot of heat, and it also doesn't warp whenever it gets hot, right? It's good for thermionic emissions. So some of the same reasons that we use it in the target, but for different reasons as well. In the target, we use it because it's a relatively high atomic number and it takes high heat, right? In the filament, it takes high heat. The atomic number really doesn't matter all that much to us in the filament, but it doesn't warp whenever we heat it up. So the focusing cup again seeks to restrict anyway the electrons to just the area of bombardment on the target. And I think that's the last thing that I edited. So filament controls, what controls the heating of the filament, that will be that lower filament circuit. If again you look in the Bushong at the circuit diagram, it kind of shows a part of that being a high voltage circuit, even though it's very low voltage. So for my purpose, our purposes here, we're going to divide the circuit into three portions. That's really two portions, the upper portion and the lower portion, and subdivide the upper portion into high voltage and low voltage sections. So that lower portion is going to be our filament circuit. So what controls it? And that's that lower portion. The purpose for the filament current is to just get us to thermionic emissions. We always have filament current going just to keep the tube warm. And we don't get to thermionic emissions until we press our prep button. So once we get to the prep stage, then we get two things. One is that we get the increase in amperage through the filament to get us to thermionic emissions, and we rotate the anode. The rotation of the anode is just in preparation of applying the high voltage so that we spread out the electrons once they bombard. So if you overuse the prep button, we talked about that on Wednesday, then what you get though is overheating of the X-ray tube. You're eventually going to wear out your bearings. So you don't want to do that. Okay, so again, in the target, I don't think this is new. I think this is in your packet that you'll pick up. So in the target, we've got tungsten, radium, and the effects on the brim spectrum, I'll just go ahead and bring that up, is that it changes pretty much everything except for the peak and minimum energy. Still, even here, the only thing that affects the minimum energy is filtration, exactly, and the only thing that affects peak energy is the applied KVP, right? But everything else is totally different. You know, just the emission of brims is totally different. You've got different characteristic spikes. So where we use targets like molybdenum is in mammography. We don't need as high KVP in mammography. We don't need to get up to 70 KVP so we have characteristic spike. We're going to use a totally different target in mammography than what we're going to use in diagnostic. I don't know when they made that change, but they used to use diagnostic X-ray tubes for mammography, and they just decided that it wasn't ideal. So they backed off and they use a specialty X-ray tube for mammo now. It's low output, low KVP. So we talked about last semester a little bit about the anode heel effect. We're going to talk about that again and more this semester. So two things about the anode heel effect. One is that what we'll get with the anode heel effect is two things. One is a difference in density, but also a difference in sharpness or recorded detail or resolution between the anode and cathode end of the X-ray tube. Right? We have and they're not the same. So what you're going to have is an increase in density on one end, an increase in sharpness or recorded detail on one end. So our negative portion of the X-ray tube is going to be our cathode. The positive portion is going to be our anode end of the X-ray tube. The component that is responsible for thermionic emission would be your filament circuit. The component that's responsible for X-ray creation would be your high voltage section. The type of interactions that account for the majority of the X-ray beam would be your brims, characteristic. You get some, but brims are going to be most of your X-ray beam. So the components that move, or the component that moves, is your anode. And most of the anode anyway, the rotor portion of the anode. So the things in the tube responsible for sharpness recorded detail would be in part your anode. It's really three things: focusing cup, the anode, and the size of the filament. So the bevel on the anode affects your sharpness recorded detail as well. Y'all remember what extrafocal radiation is? It's off-focus radiation. It's radiation that's created not on the focal tract. Okay, so you're going to have a tendency to think of off-focus radiation as one of two things, or you're going to have a tendency to confuse two things. What we're talking about in off-focus radiation would be where an electron travels across the tube, interacts on the target, bounces back towards the cathode, re-accelerates towards the anode, hits somewhere else, and makes an X-ray photon. Okay, but then failure of the focusing cup is going to cause the stream of electrons to spread out as they travel from cathode to anode. Okay, so we don't really call that off-focus radiation. What we call off-focus radiation is that bouncing electron. Okay, so we'll talk about how we kind of mitigate the problems with that. Blooming, again, is kind of like off-focus radiation, but not exactly. Blooming occurs whenever you overcharge the filament. Your space charge gets too big, you make your exposure, and it's beyond the focusing cup's ability to compress that stream of electrons going across the X-ray tube. Still not off-focus radiation. okay? Is it off-focus radiation? Yeah, it is. Are we gonna call it off-focus radiation? And the answer is no. We're gonna talk about those bouncing electrons as off-focus radiation. So what type of techniques then extend tube life? And we'll talk about that on Wednesday. If mass kills tube life. High kVp, low mass, right? Okay. So again, kVp is good for the X-ray tube, probably better for the patient. I think you'll see your technical compensation going that way. All right, so the tube envelope. When we talk about the envelope, we're just talking about the thing that holds the vacuum in, the thing that surrounds the inside components, the glass. But we've got two different types. We've got the glass and we've got the metal envelope. So the metal envelope, the benefit of the metal envelope, if you remember, is that if, well, we got to back up and talk a little bit about this first. So you've got, as tube life ages, you coat the inside of the X-ray tube with tungsten that melts off of the filament, and we call that tanning. Very good. So tanning of the X-ray tube, and glass, if you recall, is not a very good conductor of electricity, but once you coat it with metal, it becomes a very good conductor, right? So then we have a problem, potential problem with the electrons not traveling from cathode to anode, but from cathode to that tanning on the glass, right? But if they can overcome that in the construction of an X-ray tube that the envelope is made out of metal, if the travel of electrons just ignore that metal conductor that is the envelope, then just laying down another layer of metal on top of it, very thin layer of metal on top of it, it's not going to affect it. So we don't have a problem with arcing with a metal envelope. We do have with a glass envelope. We talked about the glass. If we have a glass envelope, the glass envelope is going to be made of high heat tolerant glass like Pyrex, right? So the envelope just contains a vacuum, right? It maintains the vacuum so that, you know, we don't get gas inside of the X-ray tube, or we don't get oil inside of the X-ray tube that then becomes vaporized and gassed. So the problem with a gassy tube is that it interferes with the electron travel from cathode to anode, and it gives us erratic exposures. So when you make an exposure, you want your kVp and your mass to be what you set, kVp and mass, right? So if you have gas inside of your X-ray tube, you make your exposure, you might not get what you set. So you get erratic exposures. You get exposures that don't match what it is that you set on your control panel. So what type of filtration does a tube provide? Remember, we have two different types of filtration. We have inherent and added filtration. The tanning of the X-ray tube increases that inherent filtration. The tube itself is inherent filtration even before you get to a point of your very first exposure. Remember, we don't have anything that's radioparent, it's radiolucent, so some X-rays are going to be absorbed inside of that brand new X-ray tube, never been used. The older it gets, the more, because of tanning, the more inherent filtration we get. So it does not stay consistent throughout the tube life, and that is because of the tanning of the X-ray tube. Okay, so what's the purpose for filtration? Why did Rollins start using filtration and collimation? Both for the same reason. Yeah, reduced patient dose. For the purpose of filtration, he used it to reduce the low energy X-ray photons that would only absorb inside of the patient's body. So things that add filtration is anything that the X-ray beam passes through before it gets to the patient. So you got inherent filtration, you got the glass, you got the oil, you got the port that leads into the collimator housing, you got the back of the mirror, and anything else that you put into it. So the minimum amount of filtration that you're going to have in order to legally make an X-ray is 2.5 millimeters of aluminum if you're operating above 70 kVp. Mammo is going to have a totally different set of filtration requirements, but diagnostic is always going to be that 2.5 millimeters of aluminum. Does not stay consistent throughout the life of the X-ray tube because the tanning is going to increase naturally. So what it does though is it decreases the numbers and it increases the average. So again, I like to use the analogy of tests, right? So in this analogy though, it's never going to happen, but if we had 8 tests, now throughout your lowest test grade, what's going to happen to the average? It's going to go up, right? So that's how filtration affects the average, is it gets rid of those low energy X-ray photons. So what we're left with is higher energy. So collimator housing, collimation is just a form of beam restriction. We've got a lot of different types of beam restriction. We have cones that you've probably never seen. We've got diaphragms, which you've probably never seen. But what we refer to collimation as you know it, is a variable aperture diaphragm. So what we have with the collimators are 2 sets of shutters. One set you don't see, and I'm not talking about the shutters that come in this way and the shutters that come in that way. Those 2 sets are actually one set, but there's another set on top of your collimator housing that you're not going to see unless maintenance takes the collimator housing off. And that's what we refer to as a multi-leaf. And it kind of looks like a cone, but it's a cone that opens and closes this way. Okay, so it's a multi-leaf and they kind of overlap like so. And whenever you open your collimators, they kind of spread out like this. When you close your collimators, they come closer together. So it's more of a circular type thing. And it's not really for beam restriction. It does, but it's another purpose for that is to limit the off-focus radiation. So that's how we guard against off-focus radiation, is that set of shutters limits how much radiation we have, off-focus radiation we have. So off-focus radiation, and then your collimators that you're most familiar with is for beam restriction, saving patient dose, cleaning up the image, preventing scatter from ever being created is how they affect the image. All right, so the tube housing, we've got a lot of stuff in the tube housing. It protects, against a lot of stuff. So it protects against overheating of the X-ray tube. It helps to cool the X-ray tube, both through conduction into the oil that's inside of the tube housing, but also it protects against also overheating of the tube because it's got a fan system in it, right? Maybe a bellows type system or maybe an active fan, either one. It pulls in air, cool air from the room, and it blows out hot air on the other side. So it protects against that. It protects against electric shock. It protects against rough handling. You got something inside of a liquid and you bump it into something, it's got a little bit of cushion there. So it does all that stuff, but at the same time, it protects you against leakage radiation. So if you remember back to the chapter 1 or 2 of the Bushong book, you can see where it looks like Edison is standing right next to his lab assistant doing a fluoro with an X-ray tube in what looks like a wooden box. It might not be a wooden box, looks like a wooden box. So no beam restriction whatsoever there, no filtration whatsoever. And the result was that his lab assistant, who was a friend of his, took radiation burns significant enough that it killed him. That's pretty bad. You got radiation burns to your hands bad enough that it kills you. That's pretty bad. So the protective housing limits the beam to the useful beam. So it seeks to limit, I mentioned this last semester, if you make an exposure on an X-ray tube that's not in a protective housing, it's kind of like taking a bowling ball and dropping it in a mud puddle. Where's mud go? Everywhere. It goes everywhere, right? So kind of the same thing here. What we want to do is limit that everywhere and just make it go in the direction we want it to go, and that's through the port. We do have leakage radiation though. Leakage radiation needs to be limited to 1 R per hour at a foot or so. I don't know. Amy will go through that this semester. So it helps to protect the patient against unnecessary radiation from, exposure from the X-ray tube, not from the port, right? And it also helps to extend tube life, and it does that by cooling the X-ray tube. And it also provides mechanical support for the tube. So filtration's effect on output. We're going to talk about the effects on the characteristic spectrum, minimum energy, average energy, patient exposure, image receptor exposure. So characteristic spectrum has no effect. The only thing that affects characteristic spectrum is KVP, whether or not we have one, or target material, but you're never going to change that. The effects on the minimum energy, that's what controls the minimum energy. It pushes the brim spectrum towards the high energy side, reduces patient exposure, and it does also reduce image receptor exposure. So that's an effect. We'll get a reduction. This is 2 millimeters of aluminum. This is 4 millimeters. So we lost all those X-ray photons. Some of those would make it to the image receptor. So we lose image receptor exposure, but we lose significantly more patient exposure. And then it pushed towards the high energy side. So the original purpose was limit patient exposure, pushes towards the high energy side on the brim spectrum, reduces the height, it reduces the number, increases the average, and changes the minimum to a higher energy minimum. 2 types of filtration will be inherent and added. What does it do to the average? It pushes it towards the high energy side, and what we call that is a harder beam. So a more filtered X-ray beam is a harder beam. Decreases numbers. Okay, so any questions on all that? The tube and the filtration. Okay, since that cut off, I don't know what my time is. That was another thing that I was going to get off of. That was time. What time did we start? We're probably pretty close to an hour. Let's just run through brim's characteristic. I'll spare you the drawing on the board because I think I've done that enough that you kind of get it, right? So X-ray creation, when we have brims, what we get is that slowing down. Brims is short for Bremsstrahlung, means slowing down. Law of conservation of energy is not lost, it's just transformed. So the kinetic energy of the electron that comes in, it slows down, and the result is that we get a Brim's X-ray photon. And it's always going to be equivalent to the difference between the incoming electron. It's basically going to be how much energy it loses. So the energy of the incoming versus outgoing electron, that's going to give us the energy level of that specific photon. Brim's photon creation could be anywhere from effectively 0 kVp to as high kVp as what we have set on our control panel, right? So it's just a slowing down. We lose photon energy. The energy level of the X-ray photon we create depends on the loss of that energy. It accounts for 85% of the X-ray beam, and it's essentially what's going to give us our peak energy. So most of our X-ray photons are going to be Brims. Secondarily, we have characteristic. Characteristic involves that ejection of an electron. It's characteristic of the type of target that we use. So again, if we go back to the graphic of the targets here, all these spikes are representative of different targets. Like gold has a higher brims, or has a higher characteristic spectrum. Can you use a gold target? Yeah, for a single exposure, pretty much. You know, it's going to melt otherwise. Tungsten is going to be a little bit lower, and then rhodium and molybdenum are going to be significantly lower than those. So, it involves ejection and replacement of electron. The only one that we're interested in, the characteristic energy that we're interested in, is that K shell. So we're going to make characteristic off of a lot of different electron interactions, but the only one that we really care about is the K shell, so it's 69.5. So it accounts for about 15% of the X-ray beam. I really think that 15% includes all characteristic interactions, because off the K shell you only have 2 electrons to target, right? So even though we're including all of those in that 15%, the only ones that we're interested in is 69.5. Okay? Any questions?